Hello everyone. Today we are going to cover 100% of fixed point theory in just this one video. By the end of this video, you'll not only understand how fixed point works, but you'll also write a general purpose Python program that can solve any fixed point conversion problem instantly. To start, fixed point theory is what allows you to represent numbers as ones and zeros. In digital design, there are only 4 formats to understand, which are all shown below. So what exactly is SA.B? Well, SA.B is a signed fixed point number format, and it lets us represent decimal values using a fixed number of bits in hardware. In this notation, A tells us how many bits we're working with, and B tells us how many of those bits are reserved for the fractional part. Once those two values are chosen, the precision and range of the number are completely defined, and the steps for converting a decimal value into its S.B representation is shown below. So now that we've gone over what SA.B is, now let's go over a concrete example so we can see how all of the rules apply. So in this example, we're going to show what -10.2 is in S13.7 format. So the first step in step 1 is to write 10 here at the top. Then we repeatedly divide by 2, recording the remainder each time. So 10 divided by 2 is 5, remainder 0. 5 divided by 2 is 2, remainder 1. 2 divided by 2 is 1, remainder 0. 1 divided by 2 is 0, remainder 1. Then from that, we write the result from the bottom remainder up here. So it's 1, 1, 0, 0, 1, 1, 0, 0, like that. So we have our value for plus 10. And the way we know if we can continue to step 2 is if this condition is met. So a minus b minus 1, a was 13, b was minus 7, then minus 1. So that expression is equal to 5. Since the result of step 1 had 4, and since the result of step 1, 4, does not require more than 5 bits, the number -10.2 can be represented in S13.7. So because this condition was met, we can go into step 2. Then in step 2, we write the fraction from the original expression here, which is 0.2. Then we multiply by 2 continuously until we get either 0 in our fraction or b, number of times. So 0.2 times 2 is 0.4. 0.4 times 2 is 0.8. 0.8 times 2 is 1.6. 0.6 times 2 is 1.2. 0.2 times 2 is 0.4. 0.4 times 2 is 0.8. 0.8 times 2 is 1.6. So that's 1, 2, 3, 4, 5, 6, 7 times. So then we stop, because if you go back here, stop once b bits are generated or the fraction becomes 0. In that example, we stop once the b bits are generated, because b is 7. Then in step 3, we combine the results from step 1 and 2. So step 1 is this, that goes there. Step 2 is this, that goes there. Then according to step 3, we need, after combining, we need to left pad the top left with zeros until the total length is 8 bits. So here, we need to add 2 bits to make it be 13 things long. And then we do, this a is 13. So this right here is 11 bits. We need to add 2 zeros to make it be 13, according to this rule. Then pad on the left with zeros until the total length is 8 bits. Then, because it was -10.2, we do the 2's complement to get this value. So then here at the bottom, we have our final value. So this example here is how you use this table of steps to successfully convert -10.2 into its SA.B format. So then this here is another example where we convert 80.5 into its S13.6 format. So when we do step 1, we write the integer portion here, the positive form 80, and once we repeat the steps, we get this number. But since there's 1, 2, 3, 4, 5, 6, 7 there, and so this number is 7. Then when we evaluate this expression, A is 13, B is 6, minus 1, we get 6. Well, since the result of step 1, 7, or 7 bits here, is more than 6, the condition is not met, so then we cannot go to step 2, meaning it's impossible to represent plus 80.5 in S13.6 format. So this is an example of an exception to the rule. So now let's show that same exception, but in S13.5 format. So if we repeat step 1 again, we get this value, but this time, because we have different A and B, we get 7, and 7 is equal to 7, so the condition's met. So we can, yeah, it's not greater than it, so we can go to step 2. And then the fraction is 0 after the first iteration. It's 0.5 times 2 is 1.0. So we stop, but then we have to add 4 zeros to make the result b bits long. This b is 5. Then we just repeat step 3 as we normally do, where we combine this number and this number to get this. Then we left pad with zeros to make it be 13 bits long, because that's what A is. And because it's positive, we do not need to take the 2's complement. So that's it for this one. So what is U of A? Well, all U of A is, it's just the unsigned fixed point number. And we use this table of steps to evaluate that. So here's an example of of evaluating that same number in its U13.6 format. U13.6, it just means that it's unsigned, so you can only represent positive numbers in the U format. Like, you can't represent negative something. Like, -7 cannot be expressed in this format. It has to be positive. Only positive numbers can be represented in the U format. Because 80.5 is positive, that's doable. So we do step 1, get to this number. We do the check for its table. In this table, it's this condition that needs to be met. So this was 7 bits. Since the result of step 1 does not require more than 7 bits. Yeah, 7 bits here is not greater than that number. So we can go to step 2. Yeah. And we get this value here after adding zeros. Append them. And since this is already 13 bits long, there's no need to do anything else. So then this here is the expression. So let's go back. Yeah, so from these 3 examples, we see how 80.5 can't be represented in that format. But then we show that if you use a slightly different radix system with 5 bits of fraction, it's doable. Then here we show how the same number would be represented in the unsigned format. So what about signed integer? Well, that's kind of like an SA, and it follows these rules. So here's an example of this. I won't bother saying how the steps work because it's like a much simpler version of what we've already done. You can feel free to pause the video and look at it if you want. Same thing with this one, unsigned A, that's just an unsigned integer. Steps to convert it are shown here. And here is an example of that. All right, so now that we've gone over how to convert a number into its SA.B format, let's go over how we convert a number from its SA.B format back into its decimal value. So to do that, we use this equation here, where n is the index of the current number, and the most significant bit of n gets a negative sign, and the index 0 is the digit to the left of the decimal. Okay, so in this example, suppose we're given this number. How would we know what this number is in decimal? Well, the best way, using this equation, let's just write it all down in a table. And so we do that here. And the most significant bit gets a negative sign. So we put a negative when multiplying, because at n equals 4, the most significant bit, the term that's contributed is negative value at index n, which is 1. So 1 times 2 to the n, so 2 to the 4, and it's negative because it's the most significant one. And then for 3 and onward, it's just positive. So 1 gets brought down times 2 to the 3, 0 gets brought down times 2 to the 2, 0 gets brought down times 2 to the 1, and so on. And and yeah, then you add all of those together and you get this. So this term, 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 and this term all added together gives you this. And so negative 6.8125 is what is represented by this here. Here is another one. So if suppose you're given an SA number, just a signed integer, well, you use the formula in the same way. You just don't have to deal with the fractional part. So this is how this example would work. And how do we do UA.B? So unsigned fixed point number. Well, we use this formula. It's the same formula, except it's just positive for all of them. So suppose we're given this number. What is that in decimal? Well, we just use the same formula, or we write it down. Index 0 is to the left of the decimal point. And so we write our indexes, and we generate our terms, and then we sum our terms to get this number. So this number here is equal to this. So for UA, it's the same thing again, just no decimal point. We use this formula here, but we just don't deal with everything past the decimal, so the fraction component is ignored. So when we do that, we get this number is equal to 25. So some smart tips is that if you studied the fixed point rules carefully, you should have seen that all of the problems followed a fixed set of rules that never change. What this means is that you can easily write a Python program that takes in the value for A, takes in the value for B, and then takes in any number of your choice and automatically outputs it in either SA.B or UA.B. So writing such a program, it gives you the ability to get the answer to any fixed point question you will ever have instantly. So it's worth doing, especially since it can be done pretty easily. So I'm going to show you that program right now. So once we have our Python program, we copy it as a path. Then we open up a terminal. And we do this. So let's say we have 16 bits of A, bits of B, and we do, I don't know, 30 point that. That number's that. Let's do another one. Say 14, 6, negative, I don't know, 17.4, is that. So this program will calculate the SA.B format of any number we want given an A and B. So that's that.